Good morning, everyone. I am Sukanya from BSc Chemistry on our final year. I am making a physical chemistry video for visual impaired student. Quantum mechanics. Introduction. The formation of covalent bond was explained for the first time by Jean Lewis in 1916. He suggested that a covalent bond between two atoms was formed by sharing of electron between the atom so as to complete their octet and acquired stable configuration. Further, when the atom approach each other, there are new force of interaction, attraction and repulsion between the electrons and the nuclei. The force of attraction being great than the force of repulsion result into lowering of energy. The interaction the internuclear distance at which the system has minimum energy, the stability is maximum. The distance is called the bond length. Lewis' concept could explain the stability of a molecules and that too only qualitatively. It could not answer some of a basic question as follow. Why do atoms combine to form molecules in some case but not in others? That example H2 is stable but not Ha2. Why only certain combination are possible but not other? Example H and O combine to form H2O and H2O2 but not H2O3. Why why different bonds have different bond energy? Why molecules have different shape? Example CO2 is linear while SO2 is a bent molecules. The answer to the above questions have been provided quantitatively by quantum mechanics by applying Schrödinger wave equation to calculate the properties of a system consist of nuclei and electrons. The following two different approaches have been put forward: valence bond theory, molecular orbital theory. The simplest system to be studied was hydrogen molecules ion H2 positive as it containing of only two proton and one electron. However, even for such a simple species containing of three interacting particles, no exact solution of Schrödinger wave equation is possible in classical mechanics as well as quantum mechanics. Through exact solution are obtained from hydrogen atom and hydrogen like particles like helium positive etc containing only one nucleus and one electron. Hence, in applying Schrödinger wave equation to even simple molecules or ions, certain approximation are made. One of the most important is bond Oppenheimer approximation as explained in the next session. According to this approximation, it is supposed that the nuclei being thousands of times heavier than an electron move relatively very slowly and may be treated as stationary while the electron move with a much higher speed relative to the nuclei. For example, calculations suggest that nuclei in H2 vibrate through only about 1 pm, whereas electron move with speed of a order of 1000 pm, so that the error of assuming that the nuclei are stationary is negligible. Taking the example of H2 positive ion, if the nuclei of a two atoms are represented as Ha and Hb, then in view of a bond approximation, The distance between the nuclei may be fixed at an arbitrary value r, and Skondriel wave equation may be solved for the wave function of the electron, which is at distance ra from nuclei Ha and at distance Rb from nuclei Hb. Thus, in this calculation, R is held constant and only Ra, Rb are vary. Now, a new value of a R is chosen and the calculation repeated as shown. Representing H2 positive molecules and figure 2.1. This internuclear distance R is a constant parameter in any one calculation when the calculation have been done for a number of values of R. The energy of a system may be plotted against R. The curve obtained for H2 positive is shown in figure 2.2. It is called potential energy curve because the kinetic energy of nuclei is zero as they are stationary. From the curve this obtained from theoretical calculation, the equilibrium bond length Re and bond association De can be obtained from the minimum of the plot. These can be compared with the experimental observed values. From example or H2 positive ion, the observed value of bond association energy and equilibrium bond distance from spectroscopic study have been found to be 2.78 eV, 268 kg mole and 1.06 A respectively. The calculation of the potential energy of H2 positive ion is described in the next session. Potential energy curve of H2 positive shown in figure. Calculation of energy from wave function. The Skondriel wave equation in a operator form is H psi equal E psi. Multiplying both sides of the equation with psi star and integrate over the whole space, we get this. Psi star H psi ditto is equal to form. As E is constant, the above equation can be rewritten as psi Hamilton psi ditto is equal to E psi star psi ditto. Energy is calculated. If psi is a real function, equation third can be written as E is equal to psi Hamilton. The Hamiltonian operator H is given by H is equal to H square by 8 pi square m psi plus V is Laplacian operator, which is a function of coordinate x, y, z of a electron. Thus, to obtain the value of a E for a given system, we substitute the value of a potential energy of a system and should know the correct value of a wave function, which is the solution of Skondriel wave equation. In case of hydrogen atom, there is only one proton and one electron. Hence, its potential energy is minus E square by R. In case of a molecular or ion, potential energy has to be calculated from the difference interaction between the electron and the nuclei. Moreover, in case of hydrogen atom, only one Laplacian operator is involved for the only electron present between four species containing more than one electron. A Laplacian operator is required for each of a electron. Two simple cases are described below. Hydrogen molecular ion H2 positive. Although the charged species H2 positive cannot be isolated, it is found to be present in high concentration when electric discharge is passed through the discharge tube containing H2 gas. This species consists of two protons and one electron. As shown in figure 2.1, if the two protons are represented by Ha and Hb and the distance between them is kept fixed at r, and for one particular position the electron is at distance Ra from proton Ha and at distance Rb from proton Hb, then 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 potential energy of a system is the sum of a difference electrostatic potential energy found by applying Coulomb law as under. For electron proton Ha interaction, V1 is equal to minus electron square by Ra. For electron proton Hb interaction, V2 is equal to minus E square by Rb. For two protons separated by distance r, V3 is equal to E square by R. Hence, total potential energy of H2 positive for a given arrangement of charge will be this sum of. Thus, Hamiltonian operator for a system is H is equal to minus H square by 8 pi square mv minus E square by Ra minus E square by Rb plus E square by R. Scondial wave equation for H2 positive ion is this. Second case, hydrogen molecules. Hydrogen molecules contain two protons and two electrons. For one particular distance r between the two proton are for one particular position of a two electron. Different distance are represented in figure 2.3. The potential energy of a molecules will be this. The Hamilton operator will be this, where V and V are a operator referring to a coordinating of the two electrons. Consequently, the Scondial wave equation for the H2 molecules will be Hamilton psi is equal to E psi minus H square by 8 pi square m V square minus V psi is equal to E psi, where psi is a total wave function of a two electron in a molecules. The most important quantitative that still remain to be found to obtain the value of a total energy E of a system is a correct value of a wave function. If we do not know psi, we select by the method known as variation method and return linear combination method as described below. Variation method to obtain the correct wave function. We guess some approximate wave function on a basis of our knowledge of possible electron distribution and then calculate energy E according to the equation. Similarly, if we try a number of a wave function psi 2, psi 3, etc. by considering different possible electron distribution and calculate the corresponding energy E2, E3, etc. Then according to variation principle, the following results are observed. The energy E1, E2, E3, etc. will always be greater than the value of the true energy E. The trial wave function which give the lowest value of energy is closest to the true wave function. Similarly, the lowest value of energy will be closest to the true energy. Linear combination method. This is also based on variation method. According to this method, the trial wave function for the diatomic molecules is taken as a linear combination of two wave function. Example, in H2 the two wave function are for 1s orbital. Thus in general, if the two wave function combining linearly are psi 1 psi 2 and then the trial wave function is given as this, where C1 C2 are the coefficient which can be varied. Substitute this value of a wave function equation for the energy is calculated, that is we have is equal to C1 psi plus C2 psi. Hamiltonian C1 psi 1 plus C2 psi 2 data is equal to C1 psi 1 plus C2 psi 2 whole square data. Now the coefficient C1 and C2 are varied to find out the wave function corresponding to which the energy come out to be minimum. The condition for getting the minimum of energy with respect to the coefficient C1 and C2 is that we carry out partial difference of equation 14 with respect to C1 and C2 and put the result equal to 0. Combining different results, we get a quadratic equation in E which contain the coefficient C1 and C2. This can be solved to get to value of E C1 and C2. Similarly, if the trial wave function is a linear combination of a number of a wave function with coefficient C1, C2, C3, etc., we take the trial wave function as psi is equal to C1 psi1 plus C2 psi2 plus C3 psi3. The coefficient are then calculated by variation method to get the wave function which is closest to the correct wave function, which will give minimum value of energy. The advantage of this method is that if any wrong function is included in the expansion for the trial wave function, the coefficient of that wave function will automatically come out to be 0. As mentioned in a beginning, there are two approaches to explain the nature of chemical bond and to predicate the property of a molecule such as a bond distance, bond dissociation energy, dipole moment, etc. These are a valence bond theory and molecular orbital theory. The two theories mainly differ in the fact that whereas according to VBT, atoms are considered to retain their identity and the bond is formed as a result of interaction of only the valence electron of the atom. Half-filled orbital overlap to form a covalent bond, whereas full-filled orbital do not precipitate in. On the other hand, MOT consider the molecules as a collection of nuclei and all the electrons of a molecules are distributed in different energy level around the group of nuclei, just as the electrons of an atom are distributed in different energy level of a single nucleus. Just as energy level of an atom are called atomic orbital, energy level of a molecules are called molecular orbital. Thus, according to MOT, all the atom orbital of an atom overlap with a atomic orbital of the other atom having comparable energy and probable orient. Unlike VBT, where only half-filled valence atomic orbital overlap.